Okay,
I'm gonna make a call.
we're in business. Here we go. So this is a really challenging problem, I think. So every kind of, can you wrap your head around what's going on with this?
Yep.
You've got this large conical divot in the shape of an inverted cone, right? So think like it would be like if you're in a water park and you're in that funnel that you fall down the funnel and then you go down. It's just like that, only it's not closed at the bottom, right? And it's coated with sliperium, so there's no friction. Okay, and there's an object sliding around on this cone, right? It is banked at an angle of 6.3 degrees, so it's not a very steep angle, right? So if we were to look at a cross section of this cone, it would look like that, right? And this angle right there is theta, which is 6.3 degrees, right? And then it's just this conical divot. So there's an object that's sliding around in a circular path, right? Perfect circle, uniform circular motion. And we know that it's moving with a constant speed of 45.3 meters per second. Okay? What we want to know, this is really a good problem. I'm pretty proud of this one. So here's this thing going, here's its path, right? It's going.
The more fun you have making, probably the less fun we have doing it.
Oh, I suppose that might be true. So there's the path it's making. We want to know what is this distance up the track where it's coasting, right? How far up the track is it coasting? And that's all you're given is just the banking angle and the speed. You got to tell me how far up it's moving.
How can you even figure that out?
And you can, which is what's so cool about this. It doesn't seem like you could, but you can. So let's make a free body diagram. I'm going to get you guys started, but I want you to finish this one up. You know? Tell me when to stop, because I don't want to take all the fun away. You got to be able to do some of this. You know, there's no joy if you don't get it on your own. Okay, so here's our object. What are the forces? Let's make a free body diagram. What are the forces acting on the object?
Gravity.
So gravity is pushing in which direction?
Straight down.
Straight down. Okay. Not even given the object's mass. What's other forces? Normal force, and that's it, right? The only other force acting is normal force. Okay, so the normal force is acting like so, right? Okay, and what reference frame are we going to use here? Parallel and perpendicular, or X and Y? Or you tell me, what's it going to be?
Don't you want to use X and Y?
You do. You have to use, meaning horizontal and vertical, right? You have to. And how come? It sure seems.
Because you have an angle.
Well, we have an angle, right, but in the past, now think about this compared to what we've done in the past. In the past, we definitely would have said, we're going to go parallel and perpendicular, because the motion was all going to be parallel to the surface, right? The acceleration. Agreed? And typically, like if we think back to some problems we did like that, if you look at all the forces acting, if that's theta, well, the only force that wasn't acting parallel or perpendicular was gravity, right? Everything else, if there was friction, the friction was acting parallel, right? The normal force was acting perpendicular, right? And so in the acceleration, we know the motion was going to be down the ramp, and so it made sense for us to pick parallel and perpendicular components there. But not this time, right? What's the, seen from above, it tells us that it's moving, if it's moving at constant speed, we know this thing's moving in a circle, right? Seen from above, it's moving in uniform circular motion, right? If it's moving in uniform circular motion, what kind of acceleration has to be acting on this thing? It's the only way it can move in a circle is if it's experiencing centripetal force or acceleration, same thing, right? Within a constant, right? If it weren't experiencing centripetal force, it wouldn't move in a circle. Right? That's what makes, that's the one ingredient for uniform circular motion, is there has to be a source of centripetal force to keep the thing moving in a circle, right? So here's the circle in which it's moving, and here is the axis if we want to draw. There's the axis of revolution spinning around that, right? And so in what direction is the centripetal force acting?
Perpendicular to gravity.
Perpendicular to gravity. Yeah, it's got to be acting, so the centripetal force has to be acting towards the center of the circle, and that vector is sitting in the plane of the circle, right? Everybody get that? So therefore, we've got to use horizontal and vertical, right? And really, horizontal in this case is actually centripetal, right? It's going to change. Like when the object is over there, well, the centripetal direction is going to point towards the center there. We're going to pick a convenient spot, which is right there. Yeah.
Is this being recorded right now?
Yeah.
Okay.
Yeah. Double check. Yes, it is. Okay, so we've got to then, when we set up our free body diagram, we got to break things into horizontal, meaning centripetal, and vertical components so that we can figure out what the centripetal force is, what's causing it. Okay? So let's take our body and let's break it into the components. Well, we know the mg is already acting vertically. Right? Would you agree that if this is the angle theta, then that means this angle right there is also theta, right? And if I draw a vertical in, can somebody prove to me that this is also theta? Just, you don't have to be real rigorous about it. Just give me a simple argument. It's gonna be some of that stuff, isn't it? Parallel lines. That sounded pretty good, actually.
Isn't the opposite angles are for when two lines intersect, opposite angles are equal?
Vertical angles are congruent. That's true. Okay. So you could say that this angle and that angle are congruent, right? Okay. So if their angles are the same size, we know you're onto something then, because we know that's a right angle, right? And we know that that's a right angle, right? So without getting into all the geometric formalities here, doesn't it make sense that those two have to be the same if they take the same angle and add to it just the right amount to create a right angle? And we could write this up as a proof if we wanted to, but that's not our point. I just want you to see that makes sense. Once again, a great shortcut for this is using the principle of exaggeration, right? There's only going to be two acute angles that you're ever going to see when we look at the relationships between all these angles. There's going to be this skinny one and that big one, right? Does that make sense? Is that a small angle or a big angle? Well, that's a small angle. So it's got to be the same as theta, right? Always skew it so it's exaggerated. So you've got a really acute angle and a really obtuse angle when you're, does that make sense? Okay. I mean, not obtuse. It's still going to be acute, but it's going to be one that's really close to 0 and one that's really close to 90, right? Okay. So we know that that's theta. Then does everybody agree that if I want to break up the normal force into components, because that's the only other force acting, right? It's going to be broken up into this vertical component, right, which is going to be normal force times cosine theta, and that horizontal component, centripetal component, which is opposite, so that's going to be normal force sine theta, right? So in our free body diagram, then, there's normal force sine theta, there's normal force cosine theta, right? Okay, everybody agree? So what's the centripetal force equal to? Normal force sine theta. Yeah, okay. Right, so if we set up our equations of motion then, look what we get for our equations of motion here from our free body diagram. We're going to get the y component of the net force is just, you tell me, what is it?
Fn cosine theta minus mg.
Okay, what's that equal to? Good. Why is it 0?
Because it's not moving up, floating or.
Yeah, there's no acceleration. In fact, there's no velocity even in the vertical direction, right? There's no vertical component of that. So we know that's 0. So there's one equation of motion. The other one's pretty boring. What's the net centripetal force equal to? Fn sine theta, right? So the centripetal, which I'm just going to call, well, I'll call it sub r, I guess, doesn't matter. Right, so that's equal to normal force sine theta. And what's that equal to? MA, kind of A?
Oh,
Centripetal, there we go. Right? Okay, so that allows us to solve for the centripetal acceleration, doesn't it? Right? Centripetal acceleration, if I use this second equation, centripetal acceleration equals normal force sine theta over m, but what's normal force?
mg over cosine.
Okay, yeah, look, if we solve for normal force up here, I'm going to get, I've got to add the mg to the other side and divide by cosine theta, right? So there's normal force, right? So that's going to just give me, what, g tangent theta?
Yeah.
Right, if I plug that in. So I get mg sine theta over m cosine theta. The m's cancel. And so I get g, and then sine theta over cosine theta is just tangent theta, right? Okay, so we know what the centripetal acceleration is, right? If you know what the centripetal acceleration is, and you know what the speed is, you should be able to solve for r, right?
But we're solving for,
You are, but if you know r, that's as good as knowing this distance, isn't it?
yeah.
Because look at the right triangle we're going to end up drawing. If we just take, see if we take a right triangle right out of there, doesn't it end up looking like this? Right, so if that's theta, and this is, if that's r, then this distance right here, we'll call it d, and that's what we're looking for, isn't it? But that's theta, and it's a right triangle. So if you know r, you know d, right? And you should be able to find r, because we have a relationship. What's one of our formulas for centripetal acceleration?
c squared over r.
Okay, good. Well, if centripetal acceleration equals v squared over r, we're given v. Right? Okay? Make sense? Okay, can you take a second and just forget about the algebra for a second and just think about the concepts of this. Doesn't this make sense? Would you agree that for a given acceleration, for a given centripetal acceleration, there's always going to be a correlation between velocity, speed, right? Tangential speed and radius, right? Does that make sense? The bigger the speed, the smaller the radius for that. Does that make sense for that acceleration, right? If the acceleration is, here, let's look at this again. If the acceleration is fixed, let me ask you a couple questions about this. If the acceleration is constant, if I increase the speed, what happens to the radius?
It must also decrease.
It must increase, yeah. So if I double, does everybody see that? Because if the acceleration is constant, then this ratio has to be constant, right? Does that make sense? So if I double the speed, the top's going to get 4 times bigger, isn't it? The bottom has to get 4 times bigger too. So if I double the speed, I'd have to quadruple the radius. That's what would happen, right? The circle would get bigger. Doesn't that make sense? If the object is moving faster, then it's gonna have to move through a larger It's going to, imagine that you could somehow, with a magnetic field, you had an object slipping around in this conical divot. If you could somehow make the speed larger of the object that's moving around in circular motion, if you just did it instantaneously, honestly what would happen is it would move into an eccentric elliptical orbit, right? But say we could gradually make the speed bigger so that it stayed in a circle, it would have to push further and further up the ramp, wouldn't it? Right? Yep.
Can you go back up?
Sure.
Just a skosh.
A little more. Go a little more all the way up, actually. Okay, can you describe to me where the sine and cosine theta are on that diagram? Because I see them, but I don't exactly like. The diagram's a little messy, I guess.
Yeah. So the banking angle, this is the banking angle,
Yes.
right? So in other words, like let's just say that we mill this out of metal, right? It's got this conical divot, and we mill it out of metal so that the vertex or the apex of the cone is where the thickness of the metal goes to 0. There's a tiny little pinhole there. If you hold it up, you can see light. When I set that on the table, right, if I were to slice a cross-section through the middle of this thing like so, this would be the banking angle
Yep.
theta, okay? So if you mean on this one right here?
Yes.
Oh, okay, I got you. Yeah, let's make that bigger. So,
Like I couldn't tell what you were referring to as.
yeah, that's pretty
And then
small.
sine
Yeah,
theta
let me make that bigger. Yeah, that's too small. So if this is, once again, if this is, let's say this is the banking angle theta, right? So we've got a gravitational force acting straight down, and we've got a normal force acting up at an angle, okay? Now, this is a right angle, right? And this is a right angle. Okay, so what I'm saying is that if that's theta, then that has to be theta. Okay, and there's a couple ways we can look at that. One way to look at it would be to say, if that's theta, these two lines are parallel, right? And so those two have to be theta because they're alternate interiors.
Yep.
Right? And now it's easy from there, because if that's theta, that has to be theta because those are right angles and those are right angles. Right? And does that make sense?
Yeah, no, that
Okay.
makes sense as well.
That's and the other thing you could say is those are congruent also, right? So maybe that's even an easier way to do it. If those are congruent, here, that once again, that got too messy. Let's do this again. I don't hear that. Why am I trying to draw these freehand?
That was a really good freehand line, though. It was almost a perfect line.
Okay, so there's one. Let's set this down a little bit. Oh, come on. And then let's make a vertical. Let's make a horizontal. Alright, and so then if this is, yeah, this will be easier to see. So if this is theta, then let me just copy this schematic. Okay, would you agree then by alternate interiors, this is theta, right?
Yep. And we want to cross it.
And then this one, I'm gonna go,
Is the final answer gonna be really big?
it might be. I think it'd be pretty big, actually. I think it'd be really big. Yeah, because that's pretty fast and it's a pretty small angle. So I would say hundreds of meters for sure.
Yeah, 1990.
Okay, maybe, I was gonna say maybe even thousands, yeah. And so, okay, so then, Nick, does this make sense?
Yeah,
So
no,
here-
that-
Does that help?
Yeah, my question was kind of about the, can't see my own paper. So you have the Fn cosine theta, and I understand theoretically where those forces would be applied. The green, you have Fn
Right here?
cosine, yeah, but on the left. It's
Okay.
easier to see on the left.
Yeah.
Could you go back to that diagram you just made and show me which direction?
Yeah, yeah. Okay, so this right here, this is our normal force, right? So that's the normal force, right? So if we're trying to break the normal force up into horizontal and vertical components, here's where we would do it. Right here, we would say that's gonna be the vertical component, right?
Yep.
So that's the y component. And if this is a right angle, right?
Okay.
Does that make sense? So then this one's gotta be a cosine. We gotta multiply the hypotenuse by cosine. And then this guy up here would have to be opposite, so that's gonna be sine.
Okay, that's a lot better.
Okay. And that makes sense, doesn't it? Because if you get close to zero, sine's gonna approach zero, and cosine's gonna approach one, right? So it does the right stuff. This should still be, most of the normal force is gonna be the perpendicular component here. Very small component. That's why the radius is so big, because that's a really, really small centripetal acceleration, right? So it's like, think of it as, here's the way, think about it like a really flexible rubber band, right? If I'm swinging a rock around on a very flexible rubber band, and I increase the centripetal acceleration by spinning it faster, what's rubber band going to do? It's going to stretch way out, isn't it, right? Okay. Yep.
So, the thing we got, it says for, a distance of like, so.
So you're looking for that distance right there, right?
So, what we found at that in the yellow,
So that's different. That's the radius of the circular path, right? Here's the circular path that it's making. It stays up the same height up the track the whole time. See what I'm saying? Okay. So you're trying to figure out what's that distance right there. And really, all you got to do, really what this question amounts to is if you can find the radius, then it's really not a big deal. It's just a right triangle trig thing to figure out what the length of that hypotenuse is.
oh, the,
And here's the triangle you can use right there.
okay.
Okay, because here's our circular path. Okay, it's going to go like that. Here's the other half of the.
So can we just use the opposite, or the, like 180 minus the angle,
And use this one instead?
and do sine, yeah.
Yeah, you could. That's fine. You could do that, sure. You mean 90 minus the angle?
Yeah.
Yeah. Okay? So that should get you set up for that problem. I think that's about all I'm going to say on that. Okay, so in leading up to, I got some really cool stuff to talk to you about today. I mean, this you're going to like. We're getting into some interesting stuff here. So we could find the speed of a satellite, right?
Sure.
Maybe. So what if I asked you to do that? A satellite orbits Earth 225 kilometers above its surface. What is its speed? What is its speed in orbit in its period? Right? Okay, we kind of talked about this last week, but I wanted to bring this point up again. It seems at first glance like this ought to be pretty easy, right? Because this is just uniform circular motion stuff, right? So we know that centripetal acceleration just equals v squared over r, right? And what would the radius be?
The
225 plus.
225 plus
Okay.
the radius of the Earth.
Okay, good. 225 kilometers plus the radius of the Earth, right? Okay, no big deal. That's the radius. What's the centripetal acceleration? Gravity. So what's that going to be?
Wait,
Well, a little
See,
less.
there's the
A
problem,
little less.
right? There's the part where we run into some issues. We don't know what the acceleration of gravity is up there because 9.8 is a pseudo. It's not even constant on the surface of the Earth, right? I mean,
is that at sea level?
that would be, okay, but even sea level is going to change because it's going to depend on what kind of rock is under your feet, right? And you can actually use micro accelerometers and you can make studies of what the subterranean rock strata are. Like if you're sitting on something really dense, like basalt, then your gravity's going to be slightly higher. So you can weigh a little more in Pendleton than you would if you were over something lightweight like sandstone, like on the coast.
So
Or are we
you,
getting more exercise?
So you get very slightly, yeah.
so would you weigh the least? Oh, no,
Yeah, because water would be less dense, yeah. You would, right. And so, so gravity, I mean, when we say 9.8, I mean, that's, you know, that's really not a constant. That's a pseudo constant. It's close enough. I mean, you're never going to notice any everyday calculations. It's not going to make a difference. But there are very minuscule differences that, you know, just when you move from Eastern Oregon to Western Oregon, if you were to measure very accurately the acceleration of gravity, you'd notice a little difference. Okay? But even beyond that, that's only the sort of mean acceleration of gravity on the surface of the Earth, right? That's not what you're going to get if you go above the surface of the Earth or if you were to tunnel down through the Earth, right? It's going to be different. We just happen to stay at pretty much the same distance from the center of the Earth at all times. Okay? But we got to come up with we can't do this problem, right? We don't know how to calculate the acceleration of gravity off of the surface of the Earth. The only gravity we've ever talked about to this point has been little g, right? That pseudo constant. Okay, so we need something better. We need to,
Use that.
okay, I'm going to tell you about that a bit later. Okay, so we need to come up with a law of universal gravitation that works everywhere. Okay, and this part is, the way that this was discovered or measured was really cool. This was done by Henri Cavendish. He did this, I don't remember the time, but I mean, it's a long time ago. It was at least, well, I want to say it was over 200 years ago he did this, which is pretty impressive. He effectively weighed the Earth, which is pretty amazing.
Yeah.
Think about how you could, now just contemplate this. If I just set you a task right here today without using any technology, I want you to find the mass of the Earth. Come up with a strategy without using any technology, any modern technology. How could you do that? How could you do that? I mean, weigh the Earth.
What information do you know?
You know very little, actually. You know, you would know. Okay, here's what he knew. I'll give you this. Here's what he knew. He knew what the rough, pretty good approximation of the radius of the Earth was.
How do you know that?
Okay, that's a good question. You guys could know that too. You'd have to. I'll allow the use of cell phones here and high-speed transit to expedite this process. But you could do this. So by choosing two places on Earth and measuring, having a uniform stick that you were going to put perpendicular to a flat surface and measuring the shadows, the longest shadows that were produced on a given day, you could determine what the radius of the Earth is with pretty spectacular accuracy. And that's what was actually done. So like imagine here, if we take, here's our Earth, right?
Like a sundial, but
Yeah, like a sundial, exactly. So if you go someplace, like let's say you're going to go on the solstice, if you went right to the equator, right? Is it the solstice or the equinox?
Can I write that down real quick?
What's that?
The top part, begin.
Up here?
Yeah.
Oh, yeah, you'll see that in a minute. You have to write that down. Okay, so right here, so if we take a stick and we put the stick right at the equator, and at noon on the equinox, it would cast no shadow, right? Does that make sense?
Yes.
Okay. On that same day, if somebody were up north somewhere, up here, and they had a stick, same length, exactly perpendicular to a level surface, which would be hard to do. I mean, just pour something that's going to harden. Pour some. That's what self-leveling concrete is. If you want to level a floor, you just pour kind of runny concrete on the floor, and gravity will make it a flat puddle, and then it hardens and it's perfectly level, right? So that's not hard to do. If you measure the lengths of the shadow of this one, okay, this one's going to cast a little bit of a shadow, right? So there's the shadow.
Should it be more than that?
What's that?
What is the sun?
Wouldn't it be a little bit more than that?
Yeah,
Where's the sun?
It'd be like that more. How about that? Okay.
Okay.
Because would you agree that the sun is so far away that the light's coming in parallel, essentially, right? The angle is so small as to be negligible, right? So you got to be able to do this, right? Because if we measure I gotta make this a little better so we can see this better. Let me make this larger, just so by increasing the scale, we can see the geometry a little bit better. Right, so if this is, well, that's really not gonna work very well, is it? Okay, so here's the flat surface of the Earth. So there's the length of our shadow, right? Okay, if the light's coming in parallel then, and we can measure what this angle theta is, right? If we know the length of the shadow and the height of the stick, that's a right angle. It's pretty easy to find that, right? Okay?
Pretty easy.
So then if we just continue these lines in towards the center of the Earth, would you agree that if that's the angle theta, then, let's see, if that's theta, then is this going to be theta too? Let's see. So if that's theta,
The shadow.
You did this better for me.
so, yeah, that's theta. Of course, that's theta, right? Because that's going to be,
Yeah.
that's parallel. So that's theta, right? So if you know that that's theta, and you know about how far away these two things are, right? Then you know the radius of the Earth, right? If you know that this distance right here, and this is what they did, they knew about how far they used Alexandria and some other city. And Alexandria on the solstice, it was well known that the shadows in Alexandria there were no shadows. So it was sitting on the solstice, the sun was right above it, right? And so there were people that were just professional pacers. And that's what they did. People that traveled, they would get, when they make maps, they would be able to just accurately pace out distances. Grandpa Ryan claims he can pace out a mile almost exactly. Isn't that a total Grandpa Ryan thing to do?
He might be able to,
But he's pretty close. I mean, I've watched him pace out. I mean, he's pretty darn good at it. But people would do that. They would just take standard paces and think about that. You're going to be within, you're going to be within probably 1%, 2% at the most. I mean, just try that. If you just take standard 1 yard, I do that all the time in track when I'm pacing out distances, and it's always really close. It's always really close. So a yard, and that's why a yard was made. A yard is supposed to be for a normal person. If you just walk at a brisk pace, you take steps that are about a yard. What's that? No, like 3 feet yard, yeah. Well, and they would even use things like, they would use stadia. They use these weird measurements called stadia, and I don't know what they were. But they could figure out roughly how far apart these cities were, right? And this was a city that was due north, right? So you figure out what this distance is, that arc length, and what's the relationship between arc length and angle? You guys know that. There you go. So you know that arc length equals r theta, right? So for one complete circuit, it would be r times 2 pi, right? You know what theta is, and so you can figure out what the radius is by just reverse engineering that. So that's not a big deal. I mean, we can find the radius. That was already known, fairly well known. So Cavendish had the radius of the Earth, right? And then all he had then was a pretty good understanding of electromagnetism, which people had. That was Maxwell had already developed some laws that explained, like, for example, we know what the electrostatic force is between opposite charges given distance, right, for given distances. Right? We know that opposites attract, and it's an inverse square law. And so he was able to do something pretty tricky.
I can never be a mathematician. My name's not Maxwell or Alexander.
Yeah,
Same
they're not always so exciting anymore. Here's a picture of the contraption that he used.
Nicholas.
It's called a torsion balance. This is really, a lot of this exquisite engineering of these pieces, we don't have to do this stuff very much anymore. But this thing was really impressive. So what he had these very large lead spheres that were hanging on this, looks almost like a coat hanger, right? So he's got it suspended from this beam, and this beam is attached to a strand of wire that hangs from this fixed beam up here. And there's going to be, what happens if you have your shoe is dangling at rest and you twist it a little bit? What does it do?
Push back.
It accelerates back in the other direction, right? So there's a certain torsional force, which is called a torque, that's applied when you take a torsional spring and you flex it. And that's really all a wire is, just a torsional spring, right? So he had, seen from above, this is what it looked like. He had these two large lead spheres and these two smaller lead spheres that were attached. The smaller lead spheres were attached to the torsional, the coat hanger, right? These were fixed. He would dump a known quantity of charge onto these things, and they're conductors. And so you can dump like a positive charge onto those two and a negative charge onto those two. Known quantity. You could experiment. You could put the same amount of charge, you could put it on some non-conducting materials like pith balls. I'm just gonna say that carefully. And you could measure, with the same balance, you could measure what the force of attraction or repulsion is, right? So that none of that stuff is really that arcane. He dumps the charge on there, and he measures, he knows what the force of attraction should be by using the laws of electrostatics, right? Take something light, puts them on there. Now, he's going to, now that he's calibrated his instrument, so he knows that for a given amount of charge, this thing is going to, it's going to distort by a predictable amount because of the torsion in the wire. He could shine a light off of a mirror and thereby increase the angle, and standing across the room, he could get a pretty accurate measurement of where that light hits a yardstick or a meter stick or something, right? Okay, and so he's going to be able to measure then very precisely what these small angles of deflection are when he puts on very tiny amounts of charge for very tiny forces, right? So then all he has to do is bring this thing, he's going to take this, leave this coat hanger in equilibrium where it's not moving at all. He's going to pivot the large spheres so they're fairly close to the small spheres and look for the deflection. What's causing the deflection?
Gravitation.
Gravity, yeah. Yeah, okay, here, we'll pick this up tomorrow. Finish this up.